1-0.
Welcome, everyone. This is another ACE Spotlight session. My name is Nabila, and I'm a stream owner here at ACE. For those of you that are new, if you're here for the first time, ACE is a community of machine learning practitioners and researchers who have gathered around topics in AI research, engineering, and products. We host free live sessions like this 3 to 5 times a week, and we also produce premium content in various subject areas. We currently have 14 different streams that are focused on various ML topics. This particular session is in the GNNs for healthcare stream. If you want to get some more information about it, or if you want to see the slides later after this talk, visit our website at ai.science. And also make sure to subscribe to our YouTube channel, ML Papers Explained. There you can get notified of all our live sessions and other free content. So joining us today is Dr. Edward Choi. Dr. Edward Choi is currently an assistant professor at KAIST in South Korea. He received his PhD at Georgia Tech under the supervision of Professor Jimeng Sun, focusing on interpretable deep learning methods for longitudinal electronic health records. Before he joined KAIST, Ed was a software engineer at Google Health Research, developing deep learning models for predictive healthcare. His current research interests include machine learning, healthcare analytics, and natural language processing. We're super excited to have you present here, Ed. Ed is about 13 hours away in South Korea, so we really appreciate his time. Over to you, Ed.
Hi, everybody. This is Edward Choi from KAIST. Thanks for a very nice intro, Nabila. And also, I'd like to thank Nabila for organizing this, giving me an opportunity to present my work to everybody here. So I hope this is a fun ride for everybody. All right, so today's topic would be learning the graphical structure of EHR with Graph Convolutional Transformer, or in short, GCT. We will start with a very brief intro of what EHR is, because I'm going to assume that not a lot of people are exposed to EHR. And in the same spirit, before I jump into the main topic, in the bag of codes to Graph GCT, I'm going to start with laying the groundwork on how to handle longitudinal EHR in a very straightforward manner with neural networks. And then I'm going to move to mine, which is another previous work of mine, which is the first paper to try to leverage the structure of EHR and why it is a good idea to do it. And then gonna jump into GCT, the main topic of today, which is I propose to jointly learn the structure of EHR and a supervised prediction task. And after that, there will be a Q&A session. All right, so what is the electronic health record? It's a comprehensive data set that contains everything happened to a patient at the hospital. So you go to hospital, you get diagnosis, you get prescriptions, you get like labs and procedures. That information is all stored in the hospital database. So when you go see a doctor, the doctor will pull up a screen on their monitor, and they'll typically see this kind of monitor. Like there's your name, your date of birth, your problem or your symptoms, your medication, maybe some allergies, like all these information. And EHR is not just a set of like structured codes. It's actually a very heterogeneous set of data sets. So there's demographics, such as your ethnicity, your age, your gender, your marriage status. There's medical history, of course, encounter records, medications, lab results, like blood results, like blood tests, urine tests, radiology images, such as X-ray, vital signs, billing information. So it's a very heterogeneous multimodal data set in nature, and it's not just a unordered set of heterogeneous modalities. It's actually a bit more refined. So this is a depiction of of the electronic health records in the database if you were to lay it out in a graphical manner. So as I said, EHR dataset is stored in a database, specifically a relational database in each hospital. So there are tables, and there's of course keys that links between the tables, like foreign keys and primary keys. So for example, like each patient has a unique identifier, and the patient makes visits over time, and then each visit comes with a diagnosis. Like the multiple diagnosis codes. Some diagnosis leads to medication orders, procedure orders. Some procedure order leads to like lab results. So it's a very heterogeneous, very complexly structured. I would like to see it as like a hierarchical graph, basically. And it's this graphical nature that I want to talk about today. So that's the intro. And so how to deal with longitudinal EHR in a very simple manner using neural networks. So I'd like to see patients as a sequence of visits or a sequence of set of codes. So I'm viewing visit as a set of codes or unordered set of codes. So you go to the hospital maybe 3 times, and the first visit you have like 2 diagnosis codes. You get prescribed Tylenol, and you get IV fluid. Maybe next time only 2 diagnosis codes, and the third time some other combination. So typically in the healthcare space, like classical like pre-deep learning era approach would be to have you aggregate this entire thing into a fixed sized vector, which would be like a patient representation vector. And the most straightforward way to do it is you just count everything. So like in the entire trajectory, cough twice, fever twice, IV fluid once, chest x-ray once. So you just basically count them, and then you get a very sparse counting vector, which is very horizontally very long. And then you would apply logistic regression or random forest or any like your different depending on your preference, like some classifier basically to predict something, maybe to predict kidney failure, maybe to predict heart failure, maybe to predict mortality, something basically. But if you were to use a sequence model, like in now we're in the deep learning era, if you were to use a sequence model such as RNN, 1D convolutionals, or even transformers, then you want to do it visit by visit. So again, like each visit, you can represent each visit as a binary vector, which is also again a very sparse binary vector, and you would embed it into lower dimensional space. So like the raw input vector was probably like tens of thousands of different kinds of codes, like diagnosis codes, medication codes, and you want to contract it into like 128 or 256 visit embeddings basically. And then you put that embedding into, for example, let's say RNN. You put your visit embedding to the RNN. You do it for the second visit until the last visit, and theoretically, hopefully, the hidden layer at the last time step would be your patient representation vector, because theoretically this hidden layer will contain all the experience past visits that the patient have gone through. So compared to the raw like tens of thousands of dimensional counting vector, this is a bit more like deep learning, like neural network key representation vector. And obviously you want to take that and then put into like either softmax or sigmoid function to predict something. So if you were to predict, for example, heart failure, it would be a binary prediction. So 1 being like likely heart failure, 0 not likely. So that is your like very, very basic approach. And it's been used for a lot of times in like years between like 2014, 2015 until like very recently. It's a very robust approach basically. But I was not satisfied with that approach. So here comes MIME, which is multi-level medical embedding for predictive healthcare. So it was a collaboration between Georgia Tech when I was a PhD student, IBM Watson, and Sutter Health, and it was presented in NIPS 2018. So the motivation was that I was treating, as I said, I was treating patient as a sequence of set of codes, but but I wanted to go multimodal, so not just codes, but like lab measures and clinical text and maybe even images. But so I was digging through the raw EHR data, and I figured out that the codes was not just floating around in an unordered manner, but they were like tightly connected. Like the codes had specific relationships. So if you simplify this raw EHR, you would get something like this basically. So there's a visit level, and then each visit has the diagnosis codes, and diagnosis leads to treatments being like medication procedures. Some treatments leads to lab results. So there's some data, like data sets that are well maintained, have a connection between a diagnosis and its leading like orders. So these red arrows reflect the physician's decision process. Like, oh, because of cough, I'm gonna give the patient like this and this, and because of fever, I'm gonna give the patient like this and this, something like that. So it kind of like it has the embedded domain knowledge into it. So I thought, well, now that I know that, then I can no longer just respect the way that I used to treat EHR like previously before MIME, like in my previous work like Med2Vec, Dr. I retained. What I did is I just took the embeddings of individual codes and I just summed them up, and that was my visit representation. So that was my approach. Like you either sum them or you can average them, but basically you are flattening the structure of the visit. When there was a hierarchical structure, I was just flattening everything. So it's probably not a good idea to lose the domain knowledge, the physician's decision process. So I came up with a new concept in MIME. So I came up with a new concept called diagnosis object, DX object. So this individual thing could be DX object 1. Here, cough and its related treatments form DX object 2, DX object 3 with fever, 4 and 5. So there's the DX object, like 5 different DX objects. And the way that you would derive the patient representation vector is like bottom up. So you have nausea embedding, you have cardiac EKG embedding, you combine them to get the DX object embedding, and you have like multiple DX object embeddings. So you aggregate them to get the visit embedding, and then you have a sequence of visits like 1, 2, 3. You aggregate them again with either RNN or transformer to get the final patient representation embedding. So it's like a bottom up like approach, reflecting the hierarchical graphical structure. So in retrospect, what I did is pretty similar to, it's like a special case of GCN, Graph Convolutional Neural Networks. It's just more like refined and more like tuned towards EHR dataset. But basically the spirit is the same. I wanted to respect the graphical structure, the relationship between the codes, and I wanted to use that information. So
Ed, can I interrupt you with a question?
Yeah, absolutely.
Sure. Just on that note of hierarchical structure, we have a question asking, is there normally any structure in the layers of the hierarchy, or is there a relationship between parent and child? Just when you set up the EHR?
Could you repeat the question again?
Yeah, the question was, is there any hierarchical graph structure? Is it always a hierarchy?
Oh, you mean in the EHR? I would
in the model
say,
setup.
Yeah, it would be ideal to have a hierarchy. So when I say hierarchical, that means that there is no loop, basically. So it's a directed acyclic graph. So there is no loop. And potentially there can be multiple parents. So for example, like here, there are 2 parents. So that is allowed. But having a loop, like a cycle from here to here would be, I'm not sure if that is too intuitive.
Okay.
I guess that would be an interesting, like a direction of future research, like if you have like a meta path, basically, like if you wanted to draw a new path between like the parent and maybe grandparent and the child or something like that, maybe that would be yeah.
Would that come from domain knowledge?
Yeah, obviously. So, but if you just simply deterministically transform the raw EHR data into graph, it would be hierarchical mostly.
Okay.
You can check that out in the Mimic3 webpage. So Mimic3 is an open source data set, and they provide the schema of the entire like relational database, and you can see that it is hierarchical. You always start from the patient, and then at the bottom is like very specific like lab measures and stuff.
Okay, thank you.
All right, cool. So so as I said, this was my first approach to respect the hierarchical nature of EHR. So I compared that with a bunch of different baseline methods that didn't respect the hierarchical nature. So like all the different flavors of basically bag of features approach. And I applied them, I tested them all on the Sutter Health dataset, which is basically trying to predict the future onset of heart failure based on 30,000 patient records. So my assumption is that if you know the structure of EHR so the structure of EHR, as I said, reflects the physician's decision process. So it's a domain knowledge. So if you explicitly incorporate the domain knowledge into the model, then you're basically like decreasing the hypothesis space. So I was assuming that it will probably be more robust if you use those specific knowledge in the lower data regime. So what I did here is that while fixing the test set volume, the size of the test set, I was changing the size of the training set. And obviously the MIME and the MIME variant, these two, the gap was wider compared to when in the lower data regime compared to when I was using the entire training data set. So it is like more robust when you have less amount of data and you are relying on domain knowledge, basically. So that is kind of the reason why it is a good idea to somehow leverage the structure of EHR if you know it, basically. So that's the lesson. So yeah, EHR structure reflects physician's decision process. It improves prediction performance. And I did a bunch of different experiments, but I just took one out of the paper for the sake of time management. And you can go more like you can extend this framework by incorporating more modalities like notes and lab measures and images and whatnot. So next comes GCT.
Just a question about the previous slide. So somebody asked, did you use any pre-trained embeddings for the individual codes, or how did you model that?
No, I didn't. I mean, you can obviously do that. So here they have their own embeddings like fatigue, cough, benzonatate. You can treat them as like words in NLP. So you can basically you can obviously pre-train them with, I don't know, maybe word-to-vec fashion, or even these days you can do BERT style. So You can use any type of like pre-training embeddings, and then use the relationship between the codes, the structure of EHR. That would make it even more robust to like lower data regime. That would be a great idea, actually. Yeah. All right. So yeah, moving. So next comes the GCT, which is the last project that I did while in Google Health Research before I joined KITES. So these were the collaborators. And the motivation was that, so mine was a great idea, was working okay, but it required the user to know the true structure of EHR. When I say structure, I mean the red arrows, the relationship between like the pair of codes in different layers. So MIME required you to know the true red arrows beforehand. Otherwise, you can't actually use MIME. Or you basically, if you don't know the adjacency matrix, how are you going to use the graph networks, basically? So, but the problem is red edges are not always available. Like as I said, the Mimic3 and EICU, they are the open source EHR datasets, probably the only ones out there, and both of them don't have the red arrows in the dataset. So some hospitals don't just store these red arrows in their relational database. And in addition, claims data, they usually, or virtually none of the claims data have this red arrow. So mine is not a very generalizable model. It can't be used for all EHR data sets. So that was the problem. So if the structure is known, if the red arrows are known, then you can use either MIME, which is a special model, or you can use GCN for that matter. If you don't know the red arrows, then basically what are you going to do? Are you going to just resort back to the bag of features approach? Or you can think of like GCN with the adjacency matrix of ones, but that's exactly the same as bag of features. So is this all we have, or is there a better approach? That was my question. And obviously there is potentially a better approach. So the assumption is that why don't we start with the assumption that all the codes, all the nodes in the graph or the visit is like fully connected to each other. And as we learn the supervised learning task, maybe we can sparsify, maybe we can like focus on the more meaningful relationship. So like starting from fully connected and going this way was actually suggested by Emily, who's also one of the co-authors of the paper. So after I heard this idea, I thought about the connection between the self-attention and the fully connected graph. So self-attention, like borrowing the concept from the transformer. So I'm going to assume that the input sentence is I like going to movies terminal symbol. So self-attention, the way it works is the word I is attending to all the other tokens in the sentence. And then like, again, is attending to all the other tokens. And going is, of course, so you repeat the process for all the tokens. So you have the n squared, n being the number of nodes, or n being the number of tokens, n squared number of edges, which is basically saying that transformer self-attention is assuming that everything is connected. There's a fully connected graph going on. So if you want to make it a bit more like formal, like more mathematical, add more mathematical flavor to it. So attention, the self-attention operation, the QKV operation, looks like this. So there's softmax QK transpose divided by the square root of D. So this part can be seen as this normalized attention map. And this part V is the token embeddings or the word embeddings. And this attention map is purely data driven. These attention maps are generated in a purely data driven fashion. And this attention operation, the output of the attention operation, each embedding rows are simply a weighted sum of this row and this token embeddings. So have this in mind. So knowing that, if you move to graph complements, so the graph complements, the new set of node embeddings is basically a nonlinear function given D inverse A prime XW. So A prime being the adjacency matrix plus the identity matrix, D being the degree matrix. So if you take this part, D inverse A prime, this is a normalized adjacency matrix. Or can you say that this is normalized attention map? XW is the embedding, is the node embedding. So this product is each row of this product, the embedding is basically, again, it's a weighted sum between this D inverse A prime times this one, this time this. So you can see there's like a very like one-to-one correspondence between the adjacency matrix in the graph complement, and the self-attention operation in the transformer here. And there's the node embeddings in the graph nets, and there's the token embeddings in the transformer. So there's one-to-one correspondence. And you can see that you can just view that transformer is a GraphNet with a purely data-driven fashion, and GraphNet is it's a purely domain knowledge-driven. It uses a fixed adjacency matrix over and over again. Transformer uses variable attention map over and over again, like in different blocks. So this connection between the self-attention and the GraphNet was already discovered. I thought I was the first one to know, like recognize this, but obviously there was previous works like GAT, which is graph attention nets, and also there was a lengthy survey paper from DeepMind focusing on like all the different flavors of graph nets. So obviously there were smarter people working on this like way before I did. But I thought this was like a rather nice connection, and it was well suited for the problem that I wanted to solve, which is, can we guide the transformer to learn the meaningful graphical structure? So can we guide the attention maps of transformer so that it can reflect the true structure of the EHR, the visit hierarchical graphical structure of visit? And the way I thought about it is maybe we can go hybrid. So we mix the two flavors of like purely data-driven transformer, self-attention, and the purely domain knowledge-driven GCN, the graph nets. So the way I do it is you don't start from scratch. So you start with a prior knowledge, and then you apply the attention maps. So when I say prior knowledge, I'm basing my prior knowledge on the conditional probabilities of a pair of codes. So like going through all the training set, you can calculate like P EKG given chest pain, like given chest pain, what is the probability of seeing EKG in your data set and in your visit? And given benzonatate, what is the probability of seeing QRS, which is a lab measure in your visit data? So you can calculate this by going through all the training set. And this attention map or this adjacency matrix, you can fill the cells of this adjacency matrix with the conditional probabilities. And the green cells are the like the fixed value. You always want you want to have the self loops when you're doing graph conv. So there's self loop here, self loop here. So the diagonals are self loops, and you always want the visit to be connected to diagnosis. So there's like connection there. And the gray cells are the ones that you don't allow the connections. So like you don't want fever to be connected to chest pain. So that like the outcome of this process looks a bit more like the true EHR structure. So it's very like domain knowledge driven. So you have this like you don't start from ground zero. You start from the conditional probability matrix P. So your P is kind of like the pseudo adjacency matrix, and then the following attention maps or self-attention maps, you do a regularization using KL divergence. So you start from P in the very low, in the bottom layer, in the first block, which is just a GCN with where the adjacency matrix is the P instead of the true adjacency matrix, because you don't know that. And you don't want the next attention map to diverge too much from the domain knowledge P, the prior knowledge P, and then you want to do that incrementally. So in the next attention map, you don't want your new attention map to diverge too much from the previous attention map. So you want to gradually evolve your attention map so that you're grounded to the prior knowledge, but you're also kind of like adjusting towards the supervised task that you want to do at the end, like mortality prediction task or heart failure prediction task, some supervised learning task. So there's a prediction task loss here, and then the regularization loss function here. So that is the regularization factor here. And so I tested this model on two data sets. So one is synthetic, the other is EICU. So EICU is a real world data set which does not contain the true structure, the true red arrow. So in order to prove the point that GCT can learn the true structure, I needed to like generate the synthetic one. So I generated the synthetic data set that looks as similar as possible to the true EHR structure. So I use like Pareto distribution, like the complex, like some convoluted process to make it look like real EHR data. So given the synthetic and EICU, I did for the synthetic, using the synthetic data set, since I know the true structure, I could do something like graph reconstruction. So given like a pair of codes, are there edges between the pair of codes? So you can do like edge prediction. And baselines are pretty interesting. So GCN P is purely GCN, where adjacency matrix is always just replaced with the prior knowledge, the conditional probability P. GCN random is just to prove my point that you randomize the adjacency matrix and then you apply GCN. And I want to see you want to see how it works out. Like, does true structure matter at all? And then the shallow and deep are just two different flavors of bag of features approach. Transformer is the purely data-driven. So GCT is like the hybrid of Transformer and GCMP. And obviously, if you know the true structure, GCN, then the graph reconstruction performance is perfect, basically. It's just 1.0, 1.0. But like GCT, which is hybrid of Transformer and GCMP, outperforms all the other like baseline models. And interestingly, GCMP is better than data-driven models. So you can assume that conditional probabilities well indicate or well approximates the true graphical structure. So it's a good idea to use prior knowledge, basically. So that's graph reconstruction.
Yep. Sorry, just a quick question about the Transformer versus GCT. Is the problem set up the same? Like, are you using multi-headed self-attention, and are you doing the same for Transformer and GCT?
So yeah, it's exactly. So I don't use multi-headed attention because GCN, the classical like graph convolutionals don't have multi-headed attention. It's just adjacency matrix, and you just use it. So I just try to follow the same route. So Transformer and GCT is exactly the same, but the only difference is the first layer of Transformer. I mean, first layer of GCT is replaced with GCNP. So you use a prior knowledge in the first layer, and then you use Transformer. So it's like a hybrid model.
Okay.
Does that make sense?
Yeah, I think so. It kind of addresses the question.
Cool. All right.
Thank you.
All right. So the next set of experiments is the prediction task using EICU. So I'm pretty sure everybody's familiar with Mimic3, which is like a very popular open source EHR dataset. EICU is another like sister dataset. Like it's a intensive care unit records, and it's a bit larger than Mimic3. It contains about 200,000 200,000 ICU records. So I tested I applied two prediction tasks. So one is readmission prediction. So given the current ICU admission, will you be readmitted to this ICU again within the same hospital stay? Mortality prediction is, will you die during the ICU stay? So for the readmission prediction, GCT outperforms all the other. I mean, in both cases, GCT outperforms other models to varying degrees. But in readmission prediction, compared to GCT and the next best model, you can see there are some gaps. But in the mortality prediction case, it is like approximately the same. So like the difference is very marginal. So the takeaway message is that some prediction tasks require like well curated domain knowledge. Like it depends on the graphical structure, but some tasks not so much. So like one of the future works is to apply this approach to like a bunch of different tasks and see if like which tasks are more dependent on the graphical structure and which are not. So that would be an interesting future way forward. Right. So this is the next part is a bit more qualitative. So I wanted to see if the attention maps are really learning the true graphical structure of EHR. So obviously I need the ground truth graphical structure. So I use the synthetic data set here. And this is a Transformers attention block 1, 2, 3. So attention map from block 1, map from block 2, map from block 3. And this is the attention map where the main character is this one, a small box here. So this guy is attending to here, 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 here. Basically, so the red bars are the true edges, the true connections, and the blue bars are the attention maps. So there are like, I don't know, like 20, maybe 25 different codes in this specific example. And this guy is the main character, and we're trying to estimate we're trying to like approximate the true graphical structure by purely doing purely data-driven fashion. So in the first block, obviously, this guy doesn't know where to attend to, so it just uniformly attends to like all the different codes. And then in the second block, this guy kind of picks up the signal, like a very significant amount of attention is applied to these two, which are true connections, but it is missing the other ones. And then when you go to block 3, now it is like attending to all different, like the ones that are not actually connected. So like it is a lot of energy are being poured towards here instead of here. So this shows that Transformer is not real. So I was doing a graph reconstruction test for this, and when you're doing this and jointly learning the graphical structure, it is not doing a very good job. But when you use GCT, you start with a prior knowledge. So prior knowledge, which is the conditional probability. So a lot of there's a forced scalar value here, and then there's a very high conditional probability assigned to given this, what is the probability of this? So heavy attention, heavy conditional probability port tellers here. And when you move to the second block, it is a bit more, it is like adjusting a bit more. So it is decreasing the power from here and then trying to readjust to the true ones. And in the block 3, now it is like properly attending to the true connections. I mean, although there are some like residuals here and here, but it is compared to Transformer, it is doing a way better job. So that is why like GCT is handling the graph reconstruction task like much better than Transformer. And of course, it is doing a better job for readmission task and mortality task. And I did a bunch of different tasks. I just chose like a couple for the time management purposes. So yeah, this was kind of like a visualization to show that the GCT is doing a rather good job of approximating the true graphical structure. So the lesson is, even if we don't know the true structure, there's a still better way than just to treat everything as bag of features approach. So like a hybrid of Transformer and GCN is one of the things that you can do, which I propose. And the next, like the few future works would be how to handle evolving or dynamic graphs. Like you go to hospital and then as you stay in the hospital, your graph or your connection between the different like codes will change over time. So how can you address that? How can you model that over like a continuous timeline? That would be an interesting path. And of course, expanding to more modalities. Again, like trying to incorporate notes, images, demographics, like sensor images. That would be also an interesting way forward. All right, so yeah, this is the end of the talk. Thanks for listening.
Thanks so much, Ed.
I hope it was fun. Yeah.
A couple of questions on your conclusion slide, I guess. So somebody wanted to know about what would you do when you have multiple edges? And so I guess on that note, multiple edges could be maybe multiple visits or your dynamic graph, like it ties in with that. How would you handle for that? Would that be like self-attention heads, like have multiple heads to deal with that?
So when you have multiple visits, that's a very good question. So here, what I did is all these like experiments were done on a visit basis because I wanted to make it more simple so that there's a like confounding factor. But actually, patients have a sequence of it. I'm sorry. Yeah, patients have a sequence of visits. So once you derive the visit representation using GCT, you should come up with a way to aggregate like a sequence visits again, either using RNN, 1D covenant, Transformer. That's up to you, but you should come up with a way to aggregate the visits and then get the final patient embedding vector. So that's obviously something you should do. And what was the other question? What was it about the multi-head attention?
The question was more so if you have multiple edges between nodes, I guess. And I was thinking the multiple edges could be multiple visits, but it seems that you're modeling visits differently. Like every visit is its own embedding. So I guess we can scrap that, and you've kind of addressed that. But so the question was more on if you have multiple edges in your graph structure, like here you have only one edge going to each node, how would you handle for that? And the assumption from the person was just wondering if you can use self-attention and like multiple number of heads from like the attention perspective to handle for that. What do you think?
So I'm gonna assume that the question was about like, what if there were different types of edges? Like,
yes,
the edges here are all like parent-child relationship, basically. Like something is connected to something, or like the parent is connected to child is connected to grandchild, something like that. But there could be different types of edges, obviously. So this edge here is prescribing medicine, but this edge here is ordering procedure, which is semantically different. And then this again, this edge is like ordering a lab, which is again semantically different. So in that case, it is probably a good idea to actually prepare a different embeddings for different relations. So there could be like a relation embeddings for parent-child relationship. There could be relation embeddings for medication orders, separate another embedding for like procedure orders, like different types of different like a whole different set of like relation embeddings. That would be an interesting approach. I mean, I didn't do it, but that's basically a very like a straightforward idea that you should do when you want to model EHR in a more like accurate manner. So that would be a one way. Yeah.
Cool. Thanks for that. Here's just another question over here. How are the gradients scaling for the embeddings at different parts of the hierarchy? Question is, are there any processes for normalizing the scale during training?
Scaling the gradients specifically for different hierarchies, like different layers. I mean, different like depths.
I believe so. Yeah, I think that's what the question is asking. So So is there anything you do in training that's a little different to handle for like?
Not exactly. I'm not sure if that is necessary. Like if you think about transformer or GCN, I don't. It's just like everything can be represented as an adjacency matrix, and the adjacent. Just looking at the adjacency matrix, it doesn't distinguish between different depths. It's just that whether something is related to connected to one another. So in that case, I'm not sure if layer specific gradient scaling is like the best idea. I'm not really sure about that.
Okay. Would you say you run into that though? Because for multiple layers, you do have like your adjacency matrix is sort of changing to some extent.
Oh, right, it is changed. Yeah. So okay. So I thought maybe we were using different terms. So when I was saying different depths, I was talking about the depths in here, like depth 1, depth 2, depth 3, depth 4. I was addressing that whether you should have gradient scaling for different depths, but so obviously that's not the question you were looking for. So in different different blocks. Okay, so like the jth block, there's the prior there's conditional probability matrix block, then there's like a self-attention block, another self-attention block. And I was basically doing just scale divergence between the attention maps to regularize. I didn't do anything specifically to scale the gradients between the convolution blocks or self-attention blocks. Maybe that could, addressing that would be probably, it would like stabilize the learning process, but I didn't really find the training process to be unstable very often. It was training rather well. So I didn't really think about gradient scaling.
Okay. Cool. I guess a question from my end. It seems though, like we start with the assumption that everything is heavily connected, and as the model learns, it gets more and more specific. So do you ever run into this situation where at the end of the training process, your new adjacency matrix is super sparse? Does that happen? And I guess in some situations it's good, but it could also be bad, right?
Actually, that's a very good question, because one of the limitations of this model is that the adjacency matrix or the attention maps need to be normalized. So you need to have some connection. So there can't be zero connection. It's either that you're connected uniformly to everything, or you're focusing on some like a subset of the codes, because it's normalized to be the probability of 1. So that's kind of a limitation. Like sometimes you don't want to have any connections, but this model doesn't allow that. You need to be at least connected to everything.
Okay, so I guess, is that the purpose of adding those self loops at the beginning?
No, adding the self loops is just to make the propagation of the errors when you have the GCT, when you have the graph convolutional, without the self loops here, the self loops being the diagonals here, if you set these to 0, then when you like multiply this weight, when you do the weighted sum of this times this, you won't be retaining the I itself. It'll just aggregate from the neighbors only. And then if you repeat this process again, you'll never retain your identity. So you always need to have the diagonal. So that is why I added the self loop. So it's not it doesn't have to do with like uniform distribution or something.
So I guess it just comes from the original GCN formulation.
Exactly. Yeah.
Okay. Cool. Let me just do a last check for questions, but I think we're okay. I guess while I'm asking around for any last round of questions, I have one more. You started with the assumption that, you started this probability matrix assuming domain knowledge, right? Like with the conditional probabilities. Is there any sort of ontology in the medical domain that has this hierarchy? Like I know SNOMED is a structure, but it doesn't exactly point disease to lab codes. It's more understanding medical ontology. So I'm wondering is there any other way other than this conditional probabilities to start the prior on the adjacency matrix?
I mean, that's an awesome question. So as you said, I mean, you're pretty accurate with the SNOMED description. It doesn't describe like which medications or which procedures are typically ordered because of which diagnosis. It doesn't have that. So you can, but that knowledge is universal. You can just look at any EHR with this structure to see what are the like common practice. But what you can do with SNOMED, or maybe even like ICD-9 hierarchy or CPT code hierarchy, like procedure hierarchy, medication hierarchy, what you can do is you can have a separate like a hierarchy. Like, so this is a graphical structure of EHR, but there's also graphical structure within the diagnosis codes themselves. Like diabetes type 1, diabetes type 2, they're all diabetes, right? And then it's an endocrine disease. So there's like hierarchy of diagnosis codes. So there can be another graphical structure that governs the different types of diagnosis, different kinds of like medications. So you can incorporate that domain knowledge and also this EHR graphical knowledge and have a more like, it is even more grounded to domain knowledge, basically. So that would be an interesting approach, yeah.
Cool. Thank you so much for your time, Ed. I think that's all the questions we have. So just again, to our audience, you can feel free to look up AI.science and you'll be able to access some of Ed's slides and watch this talk after the fact. There's also a link in our chat description to our NLP workshop that's upcoming. Today's the last day to get it at 35% off. Thanks again, everyone. Thank you so much, Ed, for your time. And yeah, visit us again for another Spotlight session.
Thank you very much for the invitation. It was a great time. Thank you.